And the charge,
-6 times 10 to the -6.
the particle exists in space somewhere where the potential was, I believe, 5 kilovolts. And it's going to move to another place where the potential is 8 kilovolts. And it asks, what is the velocity of the particle at the 8 kilovolt location? So I kind of arranged this just as a couple of equipotentials. Now, this problem has lots of good stuff in it, but I think that you're lacking a structure on how to attack this problem, and that's my fault. So I'd like to provide a structure for how to attack this problem. The problem, I don't know if it's clear about this, but I think the indication in this problem is that this is a closed system, so the energy of the particle doesn't change. It goes from the 5 kilovolt location to the 8 kilovolt location, but maintains the same total amount of energy. This is important because if the energy is a constant, then any change in kinetic energy plus any change in potential energy will have to equal 0. I think this is a very reasonable thing to produce, but how you apply this might be trouble. So that's why I kind of put this here. Now, before I even attack this problem, let's ask a relatively straightforward question. Do you think the particle is going to be going faster or slower when it makes it here? And before you just jump at an answer, I would be careful. I'm just going to say a few things. Remember, we're going to a place of higher potential, right? That would mean that the particle's potential energy would increase if it's a positive particle, right? This is a negative particle. So its potential energy is going to decrease. You understand? If you want to think of it as like uphill and downhill, like I tried to use as a mnemonic to try and memorize this. This is going uphill for a positive particle, but it's going downhill for a negative particle. All right? Negative particles naturally go to places of higher potential, and positive particles naturally go to places of lower potential. A negative particle will do the opposite. So, in the case of this problem, I'm pretty sure the particle is going to be going faster, or I would expect it to be going faster at the 8 kilovolt location. I would be careful about jumping at an answer. Now, right away, if this is a multiple choice question, you probably just eliminated several answers, right? It had to have, because they gave us the initial velocity of the particle, and I don't know what it was. What's that? 5 meters per second? So anything that's less than 5 meters per second, throw it away. Now, there's 5 choices, so there's going to be several choices that are probably greater than 5 meters per second, but I would imagine there's 2 that were negative, or I'm sorry, 2 that were less. All right, so let's keep going. I think you guys kind of know what these mean, but let's make sure. That's going to be K final minus K initial equals, I don't know if I can do this all in one jump, but hopefully you can figure it out. U initial minus U final. That okay? Or, probably the way I will do it, negative delta U. I'm saying it that way because I have delta V. Delta V is 8 kilovolts minus 5 kilovolts. So delta V is 3 kilovolts. And if U equals QV, then delta U must equal Q delta V. Okay, I'll keep pointing out, no new information here, right? All this stuff is stuff you had, just packaging it a little different. So I'm thinking negative Q delta V here and K final minus K initial here. Any question about those choices? So let's pull all the pieces together. 1/2 mv final squared minus 1/2 mv initial squared equals negative times negative 6e to the negative 6 times 3 kilovolts. I know the mass is 4 grams. You can deal with the mass. But this is essentially what's going to happen. This is going to be positive, which is what I would expect. We expect that our velocity is going to increase. I need that to be positive so that this side shows an increase in velocity. We have the mass, so this should be pretty straightforward to get this velocity. This is not particularly indicative of what I expect an actual multiple choice to look like on the C exam, mostly because the timing. I think they would probably ask something like, what is the particle's new kinetic energy, and not ask about velocity, because that saves a couple steps, and it's something that can be more reasonably done without a calculator if the numbers are relatively stable. So I would expect that kind of question. This adds a couple of steps, makes it outside that minute and 10-second kind of mark that we should be shooting for multiple choice. The progress checks, though, are not going to be at the same kind of pacing as a test-aligned multiple choice question. All right. Yeah. This is the big thing. If you're dealing with a system in which the energy is constant, any change in one energy has to have an equal and opposite change in the other energy. Although we've talked about that as a mechanics topic, I generally don't trot this out as much. I probably should, because it's pretty easy to understand this way. All right. So let's, for the time being, assume that there is a applied potential difference between A and B that is unchanging. So, in fact, let's put some numbers to this just for fun, but then we'll talk about it as a non-numerical question. So let's say the area of the plates is 2 meters square, and we'll just use everything in terms of epsilon. So just leave epsilon in the answer. And the separation distance of the plates is 0.1 meters. All right? If I apply 120 volts between the plates, based on your work so far, you should be able to use what's here to tell me the amount of energy stored in this capacitor in terms of epsilon. So just to make sure you can, could you try that real quick and prove to me that that's true? So based on this applied potential difference and this structure for the plates, and assuming it's an air-gapped capacitor, can you tell me how much energy is stored in the plates in terms of epsilon? Not terrible. Now, of course, you put in E, and that incredibly big number goes to like not very much, right? E is times 10 to the negative 12. So there's not a whole lot of actual energy here, even with a 120 volt source. How much force would it take to try and pry one plate away from the other? Now, I know you guys tend to think I'm asking something really bizarre. This is not that bizarre. I want to just point out one thing, and it should be enough for you to be able to launch right into it. We're dealing with capacitors. They're all about charge. I don't want to do this for you. I want you guys to try and put these things together. I will give you a little bit. We know one plate's positive, one plate's negative. Clearly they're being pulled together. How much force is that? hear me out. Although you guys are putting numbers in, as I tried to say to at least one table, the number really is useless garbage, right? The only thing good about having a number is it's something that I can easily compare table to table. I have a few students who have no idea what to do here. I have a few who probably are jumping right into it. My next question requires that you understand the last two things we've talked about. And that's what's hard, is I don't really know if you do or not. But what I want to ask is, if I tried to pull this away, first, would the force necessary to do so increase, decrease, or stay the same as I'm pulling it? And I don't know that it's something that you can jump to. You've done all the work to be able to answer this. In fact, if you had done this work without putting in numbers, you would probably have an answer that would tell you. Maybe go back through, leave the numbers out, and put together a symbolic relationship of force in terms of area, separation distance, voltage, epsilon. I think you can do that. And I'm going to do the same thing. And that's because I have people in the room who can't do it. So for me, the start is here. I need to know the charge on the capacitor. I want to start there. I need to put it in terms of other things because I don't think the charge on the capacitor is going to stay the same. Since charge equals C times V, I know the potential is going to be the same. That's staying constant, an applied potential difference. But as I pull the plate away, I know that the distance between the plates is going to change, and that's going to reduce the capacitance. So as I pull the plates apart, pretty sure the charge in the plates is going to change. It's going to go down. In fact, we can see that right here when we put those things together. Does everybody see what I've done? I'm not trying to hide anything. I combine these two things together to get a relationship that tells me the charge on the plates in terms of the shape and size of the plates and the applied potential difference. Any question? Does it clearly show that if I pull the plates apart, the charge on the plates goes down? That's a yes or no question. You can say that. If it doesn't clearly show it, I can highlight the part that's clear. All right. Well, let's talk about electric field for a minute. The electric field between the parallel plates is uniform, right? It's the same value everywhere between the plates, but it's based on the charge. So though it's a uniform field, if the charge goes down, the electric field's going to change. I think the next thing you should probably do is come up with an expression for the electric field. But the electric field is based on sigma, which is charge. So I combine these together. Any question about that or what I've done? All right. I can combine these together now. Correct? When I combine these, I want to be careful. I'm putting this where Q is. And you're going to laugh in a minute, but we already had this from the very beginning. Do you see it? If you don't, allow me a quick reminder. You do remember that from a long, long time ago? So we could have maybe avoided all of this. I didn't mean to steer you out of the way, but I did kind of mean it. We didn't have to start here. We could have started with this. For a uniform field, that would have been true as well. Not trying to be mean, but it works this way. It's kind of nice. All right, we've got the electric field. I think our next step is to combine these two things. Don't you? That'd be a good place to go. So the Q is the charge on the plates. The electric field is V over D. So the force required to pull the plates apart is going to be I'd argue that it's pretty clear the force is going to drop a lot, isn't it? Pretty fast too, don't you think? Now, I have a question for you guys. I think it's an interesting question. I'm trying to pose this as questions. And I hope that you're not seeing, I'm showing you what I hope is an interesting way these things are related. Do you think the energy in this capacitor goes up or goes down as you pull the plates apart? I'm not trying to be deceptive, and I'm not trying to confuse you. Go ahead, Sergio.
I think it goes down.
I think it goes down too. And I think we can see it right away. 1/2 CV squared. That's the energy between the plates, right? Does the capacitance increase or decrease as we separate the plates? It decreases. V stays the same, C decreases, the energy goes down. Right? No doubt in your mind? What I would be interested in finding out, you could find delta U for separating the plates. Right? Say maybe have the plates go from D to 2D. Just pick some random places to start and finish. I'm wondering, if I wanted to calculate the work to do the same thing, couldn't I do it this way? Couldn't I integrate based on the changing force, how much work is done to separate the plates? Shouldn't it be the same amount? We have an expression for force, and you have an expression for how to calculate the energy. I think this would be an interesting exercise. Interesting enough where I'd like you to try it. Maybe like over the weekend. I'm thinking it's about 5 minutes of work. To do it correctly for this, if you want to use it, insert X for D. So you have a variable of integration, since X represents the displacement that you're going to go upon. You guys follow what I'm saying? So this would be the integral from D to 2D of A epsilon naught V squared over X squared dx, evaluated from D to 2D. And then just compare it to this one. All right, there's only one thing we didn't do, and maybe that's because I'm being slow or taking my time. If you put a piece of metal in between here, do you think that really does much to your capacitor? I want you to think on that this weekend. It will make a difference.